In this problem, we're given two diverging lenses, and each of these lenses has a focal length of 12 centimeters. The lenses are also separated by 12 centimeters, and that means that two of the foci are landing on the lenses. So if I label all the foci with which lens they belong to, here's lens number 1 on the left, and there's one of its foci, and here's the other focus landing right on lens 2, and then the foci that belong to lens 2, well, one of them lands on lens 1, and the other one's to the right of lens 2. And we're placing an object 6 centimeters from lens 1. We can see on the grid that that's 3 spaces. That means each of these spaces represents 2 centimeters. And our job here is to make a complete ray diagram using 3 principal rays at each step. So we're going to process the image through lens 1, and then we're going to use that image as the object for lens 2 and get a final image out of this. After we approximate the image distance and magnification using the ray diagram, we're going to back it up with the algebraic calculations using the thin lens and magnification equations. So we start with the principal rays as we process this thing through lens 1. And I start with a ray coming horizontally off the head of that object. And that's going to be refracted away from the principal axis so that it comes from the direction of the focus F1. The next ray that I'll choose is the one that passes through the center of lens 1. And that's unrefracted. And then finally, I'm going to choose the ray that aims at the far side focus for lens 1. And that ray is going to be refracted horizontal to the principal axis. So we're going to use a dashed line to remind us of the direction that ray was originally aimed, but the light ray doesn't actually go that way, so that's why it's a dashed line, and the refracted ray coming out horizontally. Now on the right side of this lens, we see 3 diverging rays, and so what we do is trace back and find a common origin for these 3 rays. And we already have the traces for 2 of these, the one on top and the one on bottom. But the one in the middle doesn't have a trace back to the direction that it originates when we observe those diverging rays. And all 3 of those should intersect at the same point. That's a nice way of checking our work and making sure that these principal rays all make sense. And there's our first image. Now because this lands to the left of lens number 2, we can go ahead and just process that first image as if it is the object for lens number 2. There's another case you have to be careful of, where if the first image lands on the opposite side of the second lens, you can't treat that first image as the object for the second lens. And I'll post a link to the video where this case is covered. It's called the virtual object case. Well, fortunately, we don't have to deal with that here. Okay, because we're allowed to use the first image as the second object, we can go ahead and just start processing the principal rays from the first image through the second lens. And the first thing I do is take a ray coming horizontally off of that. That's going to be refracted away from the principal axis from the direction of F2. That's one of the foci for the second lens. Then the easiest one, of course, is the ray that passes through the center of lens 2. That's unrefracted. And then finally, we have the ray that's aiming at the opposite focus. And again, that one is refracted parallel to the principal axis. So again, we see 3 diverging rays to the right of lens number 2, and we want to trace those back to a common origin. I can already see where this is supposed to be because the intersection of 2 of those is right here. And then I just trace back the third ray to verify that it lands in the same spot. So I'm tracing backwards from that third ray. All 3 of those do intersect at a common point. So I'm confident I've got the right spot. And my final image ends up right here. And now we can get a geometric approximation for the final image distance relative to lens 2 and the total magnification of the image. So remember that every grid space on this grid is 2 centimeters. And I count 1, 2, 3, and a little bit. It looks like slightly less than 7 centimeters for this image distance. I'm just going to call it like 6.8. I'm going to call that DI2 because it was the image formed after processing through the second lens. That counts as a negative because it's to the left of lens 2. So I'm going to call it negative 6.8 centimeters. Then my total magnification, I like to use a capital M for that. You would find that by taking the final height of this second image and dividing by the original height. So the original object had a height of 4 spaces on this grid. The final image is slightly over 1 space. So I could call that about a 1.2 spaces for the final image. So 1.2 over 4 for our total magnification. And this gives us approximately 0.3. The fact that it's positive means the image is upright. And then 0.3 means it's only 30% the original height. Next, we want to get the algebraic solutions. So this means finding the image location using the thin lens equation and then finding the magnification at each stage using the magnification equation. So we have to split into two parts here. There's the processing of the first image and the processing of the second image. So when I write down the thin lens equation for the first part, I'm going to write 1 over dO1, that's the object distance for the first lens part of the process, plus 1 over dI1 is equal to 1 over F1. Well, this means 1 over dI1 is 1 over F1, and F1 is 12 centimeters, but it's a diverging lens and we count that as negative. So I have a negative 1 over 12 and then minus 1 over dO1. Well, the object distance there, the object was 6 centimeters from lens 1, so I have minus 1 over 6. So I combine those numbers on the right in my calculator, then I take the reciprocal of the result to isolate dI1. And when I run the numbers on this, I get negative 4 centimeters. I can also find the magnification for the first stage, and I'm going to call that little m1, and that's the negative of the image distance, which is negative 4. So this magnification is going to come out positive, and then divided by the original object distance, which was 6. So I end up with a positive 4 over 6, or 2/3. Now we have to process that first image as the object for the second lens. And the first thing we have to deal with here is that the object distance is not that 4 centimeter value. It's the distance between that first image and the second lens. And that's 12 centimeters. That's the lens separation plus the additional 4 centimeters. So that's 16. So dO2 is going to be 16 centimeters. Then I plug into the thin lens equation and I have 1 over dO2 plus 1 over dI2. That'll be the final image distance relative to the second lens is equal to 1 over F. This means 1 over dI2 is going to be, again, negative 1 over 12 because the focal length of the lens is negative 12 centimeters. And then minus a 1 over the object distance, which we just figured out was 16 centimeters. Run the numbers on this one, and we find that dI2 is negative 6.86 centimeters. So that's the real answer, and we can go back and check with our geometric approximation to make sure it's pretty close. Our approximation was negative 6.8 centimeters relative to lens number 2. We got negative 6.86, so this is pretty close. Now the magnification for the second stage is again a negative image distance, so there's double negative there. 6.86 over the original object distance, which was 16. This gives me a magnification of 0.43. Now the final thing we need to do for this problem is find the total magnification and compare to what we got from the ray diagram. And the magnifications just multiply at each stage. So I have the total magnification should be m1 times m2. m1 we wrote as an exact fraction, that was 2/3. m2 we wrote as 0.43. And when I run the numbers on this, I get 0.287, which is also a close match for the approximation that we made using the ray diagram. So everything looks good and we're done with the problem. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.